Okay, there are few more techniques which are also called downstream, but they are not very adapted in very large scale. Techniques like absorption, distillation and so on. So, I will briefly touch upon that, and then later on we will look at the future trends or how the research in downstream is going to go towards. Okay. The absorption is a important technique, especially to trap the gases leaving a bioreactor or a fermenter. So, there could be carbon monoxide, carbon dioxide, methane and so many other toxic gases also that could be produced during fermentation. You do not want it to just vented into the atmosphere. So, generally the gases are bubbled through a absorbing liquid. This liquid could be alkali, this liquid could be water, ammonical solution and so on actually. So, the gas enters the bulk phase of the liquid and this is trapped, okay, that is called absorption. Sometimes the gas may react with the liquid or sometimes it may be just getting absorbed. This is also called scrubbing. Chemical engineers have been using this term scrubbing for a very long time, but in bio we do not use much of that actually. So, this is almost similar to adsorption where the phenomena is surface dependent. So, you have a gas or a liquid getting adsorbed on a surface of a catalyst or a particle, whereas in absorption the gas getting trapped in bulk of the solution. Okay. So, that is the main difference between absorption and adsorption. So, the most important law here is Henry's law, you must have studied long time back. The concentration of a gas that dissolves in a liquid is proportional to the partial pressure of the gas, okay, over the liquid at low dilution of course. So, we have a relationship which connects the partial pressure of that gas above that liquid and the concentration of the gas, okay, in the liquid, okay, and that is given by the Henry's law. So, Pa, that is the partial pressure, K is the Henry's law constant, Xa is a mole fraction of that particular component, that is given by Ca by Ct. So, Ca is the concentration of the gas that is in the liquid and Ct is the sum of concentration of all the species. So, you may have many species, okay, that is why Ca by Ct is called the mole fraction, and this is valid only in dilute condition and this is called the Henry's law constant, okay, Ah. This is useful because if I know the partial pressure of that solute gas in the gaseous phase, I will know what will be its concentration in the liquid phase, because both of them will be in equilibrium and that equilibrium constant is called the Henry's law constant, assuming there is no reaction. If there is a reaction, Ca will disappear into some product, okay. So, there will be more and more of the gas getting absorbed. So, this is the Henry's law constant for gases in water. For example, you can see at 20 degrees nitrogen, carbon monoxide, oxygen, carbon dioxide and so on actually, hydrogen sulfide, sulfur dioxide at 2 different temperatures. So, like that you can have 4 different gases with different fluids or liquids. There is another law that is called the Graham's law. When gases are dissolved in liquids, the relative rate of diffusion of a gas is proportional to its solubility in the liquid, but it is inversely proportional to the square root of its molecular mass. So, larger the mass, the rate of diffusion of that gas into the liquid is reduced, and higher is its solubility, the rate of diffusion increases. So, this is called the Graham's law. Generally the absorptions are done in tall towers or columns, okay. So, you have the gas mixture going in, okay, and the liquid also going into the column either in a co-current or a counter current manner, and then the gas is vented out at the top and the liquid is collected at the bottom. So, in the counter current the liquid enters, the liquid could be water or ammonical solution or alkali, and the gas that needs to be scrubbed comes from the bottom, rises and then it goes out. So, whatever gas you are interested in collecting, it could be carbon dioxide or carbon monoxide, is collected. So, the gas that is leaving will be devoid of that. So, you will get the liquid at the bottom with that particular gas absorbed. Okay. So, this is a very useful technique because from an environmental point of view, from toxic point of view, you would like to collect a gas leaving out of a fermenter, you do not want it to be vented out in the open. So, you can keep on increasing the flow rate of the gas, but then you cannot do that too much. After some time the gas velocity will be so high that it will prevent the liquid flowing down, and that is called flooding. Okay. These are very chemical engineering terminologies. So, I need to operate my gas velocity much lower than this flooding velocity, because if my gas velocity is too high, the liquid will not flow down, so the whole column will come to a standstill. So, in the x axis we have log superficial gas mass velocity, and the y axis we have the log pressure drop or unit height. So, as the gas velocity is increased, the pressure drop increases and suddenly it just shoots up, and this is called the flooding velocity. Okay. So, pressure drop increases with the increasing fluid and suddenly the pressure drop rises rapidly, reaching a loading and then the flooding. Okay. The columns are operated generally 60 to 65% of this flooding velocity. So, in a counter current operation at a certain value of gas flow, the liquid flow may stop descending, and that is what is called flooding. So, the flooding limits the throughput. So, the flooding depends on pressure drop across the column, column diameter and so on actually. So, if I have a larger column, I will be able to prevent this type of flooding. So, the pressure drop is of proportional to the velocity raised to the power 1.8 to 2 actually. Okay. So, it is pressure proportional to velocity raised to 1.8 to 2. So, another downstream is called distillation. Generally we resort to distillation in chemical processes or where the metabolites or products can withstand high temperature, especially in ethanol fermentation process. Ethanol can withstand very high temperatures, acetic acid can withstand. So, there we resort to distillation. So, distillation is based on the difference in boiling point of two liquids or difference in vapor pressure. So, the separation is based on difference in vapor pressure or difference in boiling points. So, the heavy boiling liquid or higher boiling liquid will be at the bottom, the lower boiling liquid will be at the top. Okay. So, there is a vapor liquid equilibrium relationship, and that is what it is called, vapor liquid equilibrium diagram for a binary. Binary is two liquids. So, the concentration or the mole fraction of one liquid on one axis 0 to 1, mole fraction of the other liquid on the other axis, or the mole fraction of the same in the vapor phase. So, if you consider liquid A or component A, here we have the mole fraction of component A in the liquid phase, here we have the mole fraction of the component A in the vapor phase. So, this is called the vapor liquid equilibrium. So, if I take any point here, it tells you what is the concentration of that component A in the liquid and what is the concentration of that component in the vapor. Okay. So, this is what it is, and this is the xy line. Here this is the concentration is same in the liquid as well as in the vapor. This is the 45 degrees line, that is why concentration will be the same in the vapor as well as in the liquid. So, generally you will have graphs for the vapor liquid equilibrium in this form. You can also have them in this shape also. Okay. We will look at some of those shapes actually. So, you can also plot the concentration of A in the x axis, and we can plot the vapor composition, that is the composition of A in the vapor, composition of A in the liquid. So, you can have graphs like this. So, this could be boiling point of pure A, this could be boiling point of pure B. So, A at 0%, here A as 100%. So, here you have B at 0%, B at 100%. So, this is the composition of A in the vapor phase, this is the composition of B in the liquid phase. So, 100 minus that composition will be give the corresponding composition for the B also. Okay. So, we can take any point here, okay, and then if you go to the vapor, that tells you the vapor composition and that tells you the boiling point. So, if we extend it here, come here, and go down, that will tell you the composition of A in the liquid. Okay. So, this will correspond to the composition of A in the liquid, this will correspond to the composition of A in the vapor, and this tells you the boiling point. Okay. So, this is a very useful diagram, and of course, this is useful only for binary systems. The previous graph, the vapor liquid equilibrium diagram, and the Txy diagram that is called, this is for binary. Why Txy? T is temperature, X is the composition of the A in the liquid phase, Y is the composition of A in the vapor phase, that is why it is called Txy diagram. Sometimes these diagrams will look like this. Okay. Instead of this diagram will look like this. Okay. So, what does that mean? Okay. At this point, if you see, the composition of A in the vapor and the liquid are the same. So, they are called constant boiling liquids. That means composition of the A solute is same in the liquid and in the vapor phase, and they are called constant boiling liquid, and this is called azeotrope. Okay. So, if a solution has A and B with this composition, you will not be able to separate them out at all. Okay. So, you have a high boiling azeotrope, you have a low boiling azeotrope. So, you have two species A and B. At this composition, the composition of A is the same in the vapor and the liquid phase, or the composition of A in the vapor and liquid is same. This is called low boiling azeotrope because the azeotrope temperature is lower than the pure component temperature of A and B. This is called a high boiling azeotrope because the azeotrope temperature is above the individual species boiling points. So, if you look at the VLE diagrams, corresponding VLE diagrams for azeotrope will look like this. Okay. Instead of the graph going either up or going down, the graph will cross this 45 degrees line. So, at this place the composition of the solute A will be the same in the liquid and in the vapor phase. So, if you have this composition, you will not be able to separate by just boiling at all. So, they are called constant boiling azeotrope. So, there are many examples like in ethanol water, there are certain composition range at which you will not be able to separate them at all. So, in such situations we may have to add a third component to break the azeotrope, or we may have to change the pressure to break the azeotrope, and so on actually. So, these are issues when you do distillation, especially if you have two components and they form an azeotrope, either a low boiling or high boiling azeotrope, then you are in trouble. You need to use some other method to separate them completely. So, the columns, distillation columns can be tray, can be plate, can be packed column. Even absorption columns, which I talked about few minutes back, can be tray, plate and packed. The idea of these is to bring the vapor and liquid into intimate contact, so that there is a separation taking place. So, ideal mixture is one which obeys Revolt's law. In distillation there is Revolt's law, just like Henry's law in absorption. Okay. The Revolt's law states that the partial vapor pressure of a component in the mixture is equal to vapor pressure of the pure component at the temperature multiplied by its mole fraction in the mixture. Okay. We will come to that. So, mixtures of hexane and heptane, benzene and methyl benzene, propane 1-ol and propane 2-ol, they are all called ideal and they obey Revolt's law. So, Revolt's law is partial pressure Pa of A is equal to X is a mole fraction of component A multiplied by the Pa naught, that is pure component vapor pressure of A. So, we can have Pb is equal to Xb Pb 0. Okay. So, Pa is equal to, and if there are only two species, then Pa plus Pb will be equal to the total pressure, and Xa plus Xb will be equal to 1 because mole fraction if there are two species. Okay. So, this is Revolt's law. Pa partial pressure is equal to Xa mole fraction of component A, capital P is a pure component vapor pressure. Okay. So, for an ideal, like I said, the total pressure vapor pressure will be Pa plus Pb and Xa plus Xb is equal to 1. Okay. So, you can have a batch distillation column. So, there could be a big boiler here, you put in your mixture to be separated, boil it, there is a column on top, and then this will collect lighter product, this will collect heavier product. So, in the column the vapor will flow up, the liquid will flow down. So, there is an intimate mixing between the vapor and the liquid. So, on the top you will collect light products, at the bottom you will collect heavy products. This is a batch distillation. You can have a continuous distillation column, you are continuously introducing feed, the liquid will come down, this liquid will have more heavy product, vapor will rise, the vapor will contain more of light products which is collected here, the heavies are collected here. So, continuously you are feeding something, continuously you are collecting light, and continuously you are removing heavies. This is a continuous distillation column. Okay. So, we looked at a few commonly used downstream like absorption and distillation. For the sake of completeness, I did introduce them. I did not go too much into detail, but I talked about briefly what is Henry's law and what is Revolt's law. So, we have done in detail the downstream operations, the downstream processes that follows subsequently after a fermenter or a bioreactor. Now, what does the future for downstream appears to be? So, there are a lot of literature or there are a lot of reports which tells what the experts think about in the future for downstream operations. Which are the bottlenecks that one need to focus in the downstream? That is what I will be covering for the next few minutes. So, downstream process is mandatory requirement. You cannot avoid downstream, especially in biopharmaceutical drug development, even food and so on. Actually, you have to purify your product. If you look at the market in 2009, it is about 1.5 billion downstream market, which is expected to go up to 3.75 billion. And the total reagents used in downstream, so many reagents, right? It is about 4.3 million in 2009, which is supposed to go to 6.6. So, it is a huge market for downstream process market, and it is expected to grow. Okay. So, if you look at some reports, it says 48% of USA companies and 68% of Western European companies feel that downstream processing is the capacity constraint. That means it is easy to add one more fermenter, it is easy to add one more bioreactor if I want to expand my process, but then the downstream is going to be really constraining, and it is not so easy just adding a few chromatography or adding a few separating equipment. So, that is going to be your real bottleneck. Okay. The top concerns of industry, the 2000, the day when a survey was done, they said that cost of chromatography step in purification is going to be a big issue, and the companies want to move away from protein A as an affinity chromatography ligand. So, these two concerns in the industry. Okay. When an industry survey was done, what purification steps are going to create capacity constraint? Depth filtration 32% worry, chromatography 43% worry, ultrafiltration 26% worry. So, you see that these are issues going to be in the purification stages, which is going to limit your capacity. Okay. When an industry survey was done, which will cause bottleneck in the future, order of serious problem, column chromatography, virus removal, because if you are collecting antibiotic through fermentation, you have to be very sure that the bacteria or the yeast that is producing these antibiotics is completely removed, because antibiotic is a drug. So, virus removal is a concern. Ultrafiltration, depth filtration, tangential flow filtration, clarification, sterile filtration, diafiltration. So, you see a lot of filtration issues that are going to be your worry for the future. So, one needs to put in lot of effort in process improvement, lot of effort in research and development to address these type of downstream steps. Okay. Nearly 2/3 of biopharmaceutical companies are spending for acquiring new downstream processing technologies. So, they are looking around what type of technologies are available. So 2/3, that is a big number of companies who are worried about downstream and how to acquire new technologies. Okay. So what is going to happen? Improvement expected to be in membrane processes. Okay. So the membrane, as I talked about quite a lot, is going to be improved further and further. Monoclonal fragment technology, new resins, new affinity matrices that will be looked at, better pricing to protein A. So the pricing of these specialty resins, synthetic affinity matrices is going to be an issue which is going to be improved further and further. Okay. Then comes disposable equipment and single use equipment. I think industries are also moving towards that. Can I do it one use and then throw them, because then I do not have to think about cleaning them, I do not have to think about whether there is going to be cross contamination. So disposable reactors, disposable separating columns, single use equipment in commercial scale. Okay, completely modular, mobile biopharmaceutical operations, plug and play solutions with disposable. So ready to process. So they are going to take over soon, and they are going to have lot of advantages because I do not have to think about every time sterilizing. I do not have to think about am I getting cross contamination. So use once and throw them, but the cost is still high. So the cost of those disposable equipments needs to be reduced further and further, and that is where the future is going to happen. Modular, mobile. So these are going to be some keywords in downstream. Okay. So according to Robert Blank, he is a bioprocess strategic marketing manager at Millipore. He says the future direction is integrated disposable process solutions. You may have bioreactor, chromatography, tangential flow filter, virus filtration, sterile filtration, buffer media storage and intermediate handling. So all these are going to be the future direction in downstream. So you need to address all these. Okay. Future changes in downstream, it will have changes. You are going to see big changes in affinity chromatography, alternate to protein A, new packing materials, virus filtration, cross flow membrane, simulated moving beds, single use disposables, plug and play. So the research and development and scale up and industry use is going to be in these directions actually. Okay. So few slides we looked at, and it tells you that this is where the future is going to be actually. So if you are a researcher in a industrial R&D, if you are a researcher in the fundamental institute, then you need to focus in these areas of downstream, because that is the concern for the industrial users. So we have spent about 20 lectures looking at the various principles involved in downstream processing. We did quite a lot of problems. These problems help you to understand the concepts in downstream processing, and as you know, downstream is recovery from a fermentation broth, intermediate purification and final purification. So they are very useful for biosynthetic products, pharmaceutical products, food, nutraceuticals, bulk chemicals, specialty chemicals, healthcare products, a wide number of products. You need to have a downstream purification. The level of purification could be going up from 85% right up to 99.9% depending upon whether it is a biopharmaceutical products or whether it is a bulk chemical. Okay. So after the fermentation, biotransformation, the desired product is in the cultured cells. So if it is in the inside the cells, we need to harvest the cells, break the cells and then recover the product. If it is in the extracellular medium, we can do quite a lot of downstream purification. The concentration generally will be very, very low, 5%, 10%. So we need to bring it up right up to 99%. So the downstream is the heart of any product development, and that downstream decides the cost of the final selling price of your product. Okay. So the downstream is very, very important. That is what I have been talking about in the past so many lectures. So we have the reactor, we have the fermenter here. This side I said is the upstream, where you are preparing your raw materials, you are making your media, you are sterilizing your media. Here you are having your biocatalyst, you have your microorganism, it is taken from the stock and initial growth of the microorganism. So, all these happen in the upstream, and here we have the downstream, we have the recovery section, we have the purification section, then you have the product, and of course, you also have the side products here and also the waste disposal going to effluent. So, some of the raw materials may be getting recycled, some of your biocatalyst may get recycled, especially if it is a enzyme. You cannot just throw them out, you need to recycle them for better cost effectiveness. So, the entire block diagram is called the downstream. Of course, I did not spend much time on effluent and effluent treatment strategies, but these we did spend a lot of time. Okay. So, we have removal of insolubles, which may include filtration, centrifugation, microfiltration, some membrane operations, then we have the isolation of product, cell disruption, extraction, adsorption, ultrafiltration, precipitation, then we have the product purification, chromatography, affinity chromatography, size exclusion chromatography, reverse phase chromatography. Then finally, product polishing, it could be crystallization, lyophilization, desiccation, drying. So, if the product is solid, you end up with a dry solid. Sometimes we will have a solid a liquid product, then you may have to add some sort of a stabilizing material there, which will help to increase the shelf life of the product, which will help to prevent oxidation of the product. So, these are the various downstream steps, and we looked at most of them, some of them in very detail, some of them superficially, and we did some problems which would have helped you to improve the understanding of the basic principles. These problems are also useful, as you can see, to understand the cycle concept of cycle time and the concept of scale up as well. And in the very early lectures, I talked about costing and how cost plays a very important role, and what are the various types of costs involved when you are designing a plant, because ultimately it is the cost that breaks or succeeds, especially in the area of downstream process. So, downstream is an interdisciplinary subject. As you can see, a lot of engineering, there is protein chemistry, biology, analytical chemistry and biochemistry, and the economics of the bioprocess is completely governed by downstream process technology. So, for a bulk chemical, downstream has to be very simple. For a high expensive pharmaceutical product, we can have a very complicated downstream, because it can take up the cost, because here pharmaceutical products are a high value added product will be very expensive, whereas a bulk chemical will be a low cost product. So, the total expense involved in manufacture should be very low. Okay. Thank you very much for your time. I hope you enjoyed these 20 lectures, and I hope you gained from these lectures, as well as I hope you solved some of the problems which I had given as assignments, which will sort of help you to identify important points related to these downstream. And thank you very much for your time. I hope you gained some knowledge from this short course. Thank you.